Hello. Welcome to Lecture 9 of the online course on Explainable Machine Learning and Artificial Intelligence. This is the second lecture in a series of 2 on post-hoc explanation methods specific to neural network models. In Lecture 8, we started with a brief recap on neural network models. The key idea is that neural networks learn the relevant features to process unstructured data. Moreover, we looked at the specific example of convolutional neural networks, which are used for classifying images. As you may recall, the convolutional layers extract increasingly high-level features from the input images. These features are then used by the final layers to compute logits and probabilities for different output classes. In Lecture 8, we discussed methods for interpreting the features learned by neurons in the intermediate convolutional layers. In this lecture, we will instead focus on the final layers, specifically class logits, and discuss methods for explaining the final output, how features of the inputs determine class logits. The specific goals of this lecture will be to first define saliency maps, an important class of attribution methods for explaining the outputs of neural networks. We will then review a set of different methods for computing saliency maps. We will distinguish between gradient-only and path attribution methods. And finally, we will discuss how different methods can be evaluated. Saliency maps, the central topic of this lecture, are a concept developed in the context of image classification using convolutional neural networks. So in this lecture, we will mainly focus on convolutional neural networks classifying images. But I will briefly illustrate how saliency maps can be used for other types of networks and tasks. But first of all, what are saliency maps? A saliency map is a map that highlights parts of the input image, typically sets of pixels, that are relevant to how this input image is classified by a neural network. Saliency maps are therefore a special class of feature attribution methods, which quantify how much the raw, unstructured input features contribute to the output of a neural network. Other equivalent names often used for saliency maps are pixel attributions, sensitivity maps, or feature relevance maps. More specifically, we are looking at a situation where the input to a neural network model is a set of p input features corresponding to the values of p pixels. The output of the model is a set of class logits, one logit S for each of the possible labels or classes that the network was trained to output. A saliency map is then the output of an attribution method, which generates a set of relevance scores. For each output class, the saliency map gives a relevance score to each pixel in the input image. So, very concretely, a saliency map has the same format as the input image. It associates one value for each pixel in the image. Let's look at an example. This figure shows 3 input images together with the top labels generated by a convolutional neural network: Junco bird, corn, and Wheaten Terrier, a dog breed. For each image, we can ask how much different parts of the image contributed to the output label, and this is precisely what a saliency map tells us. So here are examples of saliency maps for each of the images, where the strength of the contribution of each pixel is shown in red. How are these saliency maps computed? Well, this will be the main topic of this lecture, because there are many different methods, and each method generates a slightly different saliency map. The different columns here show the outputs of a couple of different methods. In the following, we will go through some of the methods illustrated in the previous slide. We will discuss how to compare them and how to evaluate them. Let's first start by distinguishing between 2 broad classes of methods. The first class are occlusion or perturbation methods. These methods take an image and switch off a set of pixels by turning them black. They then give this perturbed image as an input to the network and check how much the perturbation affects the outputs. LIME and SHAP, which we saw in previous lectures, are two examples of this class of methods. These methods are not necessarily specific to neural network models, as they only deal with the input and output of the black box model. These are model-agnostic methods that we discussed in lectures 6 and 7. The second class are gradient-based methods. These methods also quantify how much changing the input changes the output, but they do so by computing the gradient of the prediction with respect to the inputs. So gradient-based methods are specific to neural network models. Within the class of gradient-based methods, the different methods use different ways to compute the saliency maps. Gradient-based methods can be subdivided into two subclasses. The first subclass are gradient-only methods, which directly ask the question of whether a change in a specific pixel would change the prediction. These methods directly assign relevance scores based on gradients, so that a larger gradient for a given pixel implies a larger relevance score. In the following, we will cover a couple of examples of gradient-only methods, specifically VanillaGrad, Guided BragProp, and GradCam. A second subclass are path attribution methods, which compare the explained image to a reference image. More specifically, these methods divide the difference between the actual and the baseline prediction across pixels. In the following, we will cover one example of this subclass of methods called integrated gradients, but other examples exist in the literature such as DeepTailor and others. An important aspect is that some of these methods are complete in the sense that the sum of relevance scores they produce is equal to the difference between the prediction for an image and the prediction for the reference. Remember that this is a fundamental property of SHAP, and the integrated gradients method also have this property. Let's start with the first, probably the oldest and the most basic method for computing saliency maps, vanilla gradients, which was introduced in 2013 by Simonian, Vidaldi, and Zisserman. The idea of this method is very simple. It directly calculates the gradient of the output of the network, more specifically of the top class logit, with respect to changes in the input pixels. More precisely, if SC of I is the score of class C in response to input I, vanilla gradients perform a local linear approximation of SC of I, where the weights are simply the values of the gradient of SC with respect to the input pixel values. These weights directly give feature importance scores to individual pixels in the image. Concretely, the recipe for computing a saliency map using vanilla gradients is to first take an input image, do a forward pass in the network and compute the output class. The second step is to compute the gradient of the class score with respect to network inputs by backpropagating through the network while setting other classes to 0. And the final step is to visualize the obtained gradient by plotting a map of absolute values of the gradients for different pixels. Here are a couple of examples of saliency maps computed using vanilla gradients. These examples were taken from the original paper by Simonian and colleagues. The top row shows images given as inputs to a convolutional network model. The bottom row shows the gradient values for different pixels. Based on these examples, it looks like vanilla gradients accurately capture the area of interest, but the obtained saliency maps are quite noisy because they correspond to row gradients of individual pixels. Here are two slightly more complex examples of images that each contained two categories, a dog and a cat. In this case, we can compute two separate gradients, one for each output category, and then plot the absolute values of these two gradients in two different colors. This is shown in the panels on the right, where now red is evidence for dog label and blue is evidence for cat. Vanilla gradients are the most straightforward method for computing saliency maps. They were also one of the first methods introduced for that purpose. Most of the other methods for computing saliency maps are variants around the basic idea of vanilla gradients. One very closely related variant is guided backpropagation. This is a very popular method for computing saliency maps. It is almost identical to VanillaGrad. The main difference is that only positive gradients are backpropagated. This method was introduced by Springenberg and collaborators in 2014, and this slide shows examples from the original paper. The top row shows input images to a convolutional network together with top output classes, while the bottom row shows the saliency maps produced by guided backpropagation. The two methods we covered so far generate saliency maps at the level of individual pixels, which often look very noisy. The next method on our list, GradCam, specifically aims to address this issue. The main idea of GradCam is to avoid propagating the gradient all the way to the input as VanillaGrad and guided backprop do, but instead to propagate it only to the last convolutional layer, which is the deepest layer that retains the spatial information in the image. In a sense, this last layer provides the best compromise between high-level semantics extracted by the neural network and detailed spatial information. So the output of GradCam is a coarse localization map, which indicates which broad part of the image matters for classification. Here are a couple of examples taken from the original paper on GradCam, published by Selvaraju and colleagues in 2017. The input image is the same as in one of the previous examples. It contains both a dog and a cat, so cat and dog are the two top labels produced by the convolutional network. Saliency maps can then be generated for each of the two top labels by setting all other outputs to 0 and backpropagating the gradient. So here the second column shows the saliency maps produced by guided backprop in this case, and the two maps for dog and cat actually are not very different. The third column shows saliency maps obtained from GradCam. These saliency maps are actually big blobs corresponding to units in the deepest convolutional layer that most strongly determine the label. So GradCam seems to do a good job in identifying the overall region of the image that corresponds to the output label, but it misses all the details. One possibility suggested in the original paper is to actually combine the outputs of GradCam and guided backprop to get a more accurate saliency map, and this is what is shown in the last column on the right. GradCam is one method for dealing with the noisiness of the saliency maps produced by the gradients of the inputs. Another popular method is SmoothGrad. SmoothGrad was introduced by Smilkov and collaborators in 2017. The main idea is to remove some noise from the gradients by adding noise. What does that mean? It's basically a smoothing procedure, hence the name SmoothGrad. SmoothGrad starts from a standard saliency map produced by any method, such as vanilla gradients. It then produces a smoothed saliency map by averaging over a set of saliency maps, each obtained from an image in which noise was added to individual pixels. So SmoothGrad can be combined with any method for producing saliency maps, and it relies on one parameter, the level of the noise added to individual pixels. The final smoothed saliency map produced by SmoothGrad will depend on the noise level used. This figure, taken from the original paper, illustrates the effect of noise level on the output of SmoothGrad. The leftmost column shows examples of images given to a convolutional neural network. The different columns on the right then show the output of SmoothGrad for different levels of noise when used with vanilla gradients. Let's look at some examples. In the top row, SmoothGrad seems to produce better and better results as the noise level is increased. In the middle row, this is not so clear. Intermediate levels of noise seem to be better than weak or strong noise. Finally, in the bottom row, the largest levels of noise clearly lead to worse saliency maps. Altogether, this clearly brings up the question of how to determine the optimal noise level for SmoothGrad. The effectiveness of SmoothGrad also depends on the actual image given to the network. This figure illustrates a couple of examples for which SmoothGrad produced much better saliency maps than either vanilla gradient or guided backprop. However, the impact of SmoothGrad was much less clear for other example images, as illustrated here. In the original paper, this was assessed qualitatively, simply by visual inspection of the saliency maps. This directly brings up the question of how to compare saliency maps produced by different methods, and how to evaluate the produced explanations. But before turning to evaluations, we will cover one last method for computing saliency maps: integrated gradients. Remember that we said gradient-based methods can be classified in two subcategories: gradient-only methods and path attribution methods. Integrated gradients are an example of a path attribution method. Integrated gradients were introduced by Sundararajan and colleagues in 2017. The key idea is to compute the pixel attributions of the input image x relative to a baseline image x prime, which is most commonly just a black image. Similarly to Shapley values in SHAP, integrated gradients are motivated by a set of axioms or desiderata. The first axiom is sensitivity, and it has two parts. The first part states that for every input and baseline that differ in a set of pixels but have different predictions, a non-zero attribution should be given to those pixels. The second part states the converse. If the output does not depend on a set of pixels, their attributions should be zero. The second axiom is implementation invariance. It states that two networks are equivalent if their outputs are equal for all inputs, despite different implementations. So equivalent networks should have identical attributions. The third and final axiom is completeness. It states that the sum of feature contributions identified by a saliency map should add up to the difference in outputs to x and x prime. This axiom is directly related to the central axiom of Shapley values and SHAP. Starting from the observation that most gradient-only methods break at least one of the previous axioms, Sundararajan and colleagues designed a new method which they called integrated gradients. Integrated gradients compute attributions or equivalently saliency maps by following three steps. The first step is to consider a straight line in input space between the image x we want to explain and the baseline image x prime. The second step is to consider gradients along this line. The third and final step is to compute the cumulative sum of gradients along this line. This cumulative sum gives us the saliency map produced by the integrated gradients method. Here are a couple of examples taken from the original paper by Sundararajan and colleagues. The leftmost column shows input images to a convolutional network. The middle column shows the saliency maps produced by integrated gradients, while the rightmost column shows saliency maps obtained from vanilla gradients, meaning that the gradient was computed only at the input image and not integrated with respect to the baseline. Interestingly, the original paper by Sundararajan and colleagues proposed also a couple of practical applications of their method that go beyond usual image classification. One application is diagnosing diabetic retinopathy from retinal images. Diabetic retinopathy is a complication of diabetes that affects the eyes. Previous work by Gulshan and colleagues developed a deep network model to predict the severity of diabetic retinopathy from retinal images. In this situation, feature importance explanations can be used to allow specialists to confirm network's predictions and obtain insights for further testing and screening. Sundararajan and colleagues used integrated gradients to identify regions of interest that contribute to the network's output. Here, the image on the left shows an example image of a retina given to the network. The deep network predicts a moderate risk for this retinal image, and the image on the right shows the saliency map produced by integrated gradients. And notice that integrated gradients identify just a few pixels that seem to be lesions in the retina. The second application example provided by Sundararajan and colleagues goes beyond image processing and pertains to chemistry. It addresses the task of predicting whether a molecule is active against a certain protein. Previous work by Cairns and collaborators developed a deep network model for this task based on a molecular graph convolution architecture. In this model, an input molecule, shown on the left, is encoded as an undirected graph describing sets of atoms and atom pair features. Integrated gradients can be directly applied to produce explanations for the output of this model in terms of feature attributions, illustrated on the right for a specific molecule. In this case, integrated gradients can be visualized as heat maps over the atom and atom pair features, with the heat map intensity depicting the strength of the contribution to the output. The key idea here is that integrated gradients, but in fact also the other gradient-based methods, are not specific to convolutional networks processing images, but can in fact be applied to a variety of other deep network architectures. Integrated gradients are the last method for saliency maps that we will cover in this course. At this point, let's summarize the main advantages and disadvantages of saliency maps. Saliency maps provide visual explanations that are in principle easy to interpret. They are faster to compute than model-agnostic methods such as LAM and SHAP because they take advantage of efficient methods for computing gradients in neural networks. A large variety of methods are available for computing saliency maps. The main disadvantage, which I pointed out earlier, is that saliency maps are difficult to assess or validate, and this can make them potentially fragile or unreliable. So in the remaining of this lecture, we will look at some attempts to assess and evaluate different methods for computing saliency maps. This is really a topic of ongoing research, so we will cover two research papers that address this issue. The first research paper we will cover is called Sanity Checks for Saliency Maps. It was published by Adebayo and collaborators in 2018. This paper addresses the question of how to assess explanations provided by saliency maps and how to select a method for computing saliency map. The main idea is to use randomized tests, and the authors examined two types of tests. The first type of test, where model parameters are randomized, the goal here is to compare saliency map methods across models with identical architecture but with untrained and randomly initialized layers. The authors also use the second type of test, where instead data is randomized by permuting image labels. Altogether, the rationale is that explanations need to depend on both the data and the model. So this is a very basic set of sanity checks that can be performed to evaluate different methods for computing saliency maps. This research paper considered a series of methods for computing saliency maps, illustrated in this figure for three example input pictures. These are the methods we discussed in the first part of this lecture, and some of them are combined together. The first method is vanilla gradients, followed by smooth grad applied to vanilla gradients. We then have guided backprop combined with GradCam, integrated gradients combined with smooth grad, and vanilla gradient multiplied by the original image. The final column on the right shows the output of a simple edge detector filter applied to the image. This edge detector identifies pixels in the picture where the pixel intensity changes the most. This is not a saliency map because it generates a map that depends only on the input image and not on the output of the network. So it is not an explanation of the decision the network produces. The idea here is that comparing different saliency maps with the output of the edge detector is a good sanity check to determine how much the saliency maps actually depend on the decision of the network rather than the image input itself. Let's next turn to the two randomization tests investigated in the paper. The first one was to randomize the parameters in the neural network. Here's an illustration of how this is done. The leftmost column here shows the saliency maps obtained from a full trained network using different methods for an example input image shown on the top left. Then the different columns show the saliency maps obtained when the parameters in different layers of the networks are progressively randomized. Here, the randomization starts from the top or deepest layers and then proceeds from top to bottom layers in a cascading fashion. A visual comparison gives us an idea of how sensitive the different saliency methods are to the parameters of the network. For example, the second line shows that when combining vanilla gradients with smoothgrad, the result is not very sensitive to randomizing the very top layers, but once the middle layers are randomized, the saliency map is completely blurred. In contrast, guided backpropagation appears not to be sensitive at all to randomization. It seems to produce the same saliency map even if all layers are randomized. This illustration gives us a visual impression of the sensitivity of saliency maps to model parameters. But this can be quantified more systematically by measuring how different the saliency maps for randomized networks are with respect to the non-randomized network. A simple quantification of this difference is to compute the correlation between saliency maps and average across many input images. The final result of this analysis is shown here. In this figure, the y-axis shows the rank correlation between the original explanation and randomized explanations. A rank correlation of 1 means the two maps are identical, while 0 means they are completely uncorrelated. The x-axis corresponds to randomizing different layers in the network, starting from the top one and going towards the early layers. The different colored curves show the results obtained for the different methods used for computing saliency maps. This figure confirms the impression we got from visual inspection. The two methods based on guided backprop, shown in green and blue, produce saliency maps that are totally insensitive to the randomization of the network. In fact, they seem to depend only on the input image and not on what the network does with it. Other methods are more sensitive to the randomization, vanilla gradients being the most sensitive method in this test. The second randomization test used in the study by Adebayo and colleagues was to randomize image labels and compare the saliency maps computed on the true network model with saliency maps computed from a network trained on randomized labels. The figure on the left illustrates this approach for networks performing the classical MNIST task, which consists in identifying a number from an input image. In this case, the input number is 0. The top row shows the saliency maps obtained from different methods applied to a network trained with true labels. The bottom row shows the saliency maps obtained from a network trained on randomized labels. Clearly, randomizing labels randomizes the saliency maps produced by some methods, but not others. In this example, saliency maps produced by vanilla gradients and GradCam become almost fully random, while for other examples this is not the case. As for the previous test, we can quantify more systematically the difference between saliency maps by computing the correlation across many different inputs. The result of this quantification is shown on the right. Here, the y-axis corresponds to different methods for computing saliency maps. The x-axis shows histograms of rank correlations between saliency maps obtained from true and randomized labels. Low correlations indicate higher sensitivity of the method, And again here we see that methods based on vanilla gradients appear to be most sensitive, together with GradCAM. To summarize, this study performed some rather basic sanity checks for the sensitivity of saliency maps. It's rather striking to see that some of the models for computing saliency maps completely failed the tests. The reason for this is that edges in the input often dominate the gradients, so that saliency maps often depend more on the input image than on the output of the network. So it's important to keep in mind that a visual inspection of saliency maps is often misleading. Moreover, the study clearly pointed out the need for better evaluations, as the tests performed here were very basic. We will now move to a second study that performed more advanced evaluations of saliency maps. This study, published by Hooker and colleagues in 2019, addressed the same questions as the previous study by Adebayo and colleagues: how to assess explanations provided by saliency maps, and how to select a method for computing saliency maps. The idea this study explored was to remove from the input image the features identified as informative by saliency maps, and then check how much the accuracy of the network was affected. More specifically, their approach consisted of 3 steps. First, apply a specific attribution method to compute a saliency map. Then use this saliency map to remove pixels with high saliency from the original image. Finally, determine the prediction performance on this perturbed image. An important technical detail is that in this study they retrained the models after removing the informative features from the images to give the chance to the models to identify new features. Here is an illustration of this approach taken from the original paper. In the top left, we have an example of an input image. Then different methods were applied to compute saliency maps shown in the top row. Each column corresponds to a different method. The first column is vanilla gradients. The second is guided backpropagation. And the third is integrated gradients. Then the saliency maps were used to remove informative features from the input image. Different rows show the input image with different fractions of informative pixels removed, starting from the most informative ones. The final output of this evaluation is the amount by which the accuracy of the network changes as informative features are progressively removed. This figure shows the accuracy on the y-axis as function of the percentage of features replaced on the x-axis. The different lines show the results obtained for different methods for removing pixels. This figure shows the effects of using vanilla gradients in yellow, integrated gradients in blue, and guided backpropagation in red, and compares them with removing random pixels or applying a Sobel filter on the input image. The idea here is that a good explanation method would identify relevant pixels, so removing those should have a large effect on accuracy. Strikingly, this panel instead suggests that vanilla gradients, integrated gradients, and guided backprop have less effect than removing random pixels. This is quite surprising. This study also examined the effect of combining these basic methods with SmoothGrad and then removing the informative features, but the result was very similar. These methods still seem to do worse than random. Finally, the authors examined a couple of more advanced methods, which combined SmoothGrad with the square of the gradients or the variance of the gradient over noisy perturbations of the underlying images. These methods performed far better, as removing pixels identified by these methods had a much larger effect on the accuracy of the network output. So, in summary, removing informative features is one way of testing and evaluating different saliency maps. And these evaluation methods show that different methods for saliency maps can have very different performances. This brings me to the end of this lecture. In this second and final lecture on post hoc methods specific to neural networks, we define saliency maps. We reviewed a set of different methods for computing them. We distinguished between gradient-only and path attribution methods. And finally, we started discussing how different methods can be evaluated. One of the main messages is that it is important to systematically, quantitatively evaluate and compare the different explanation methods. How to do this is a very active field of research. In the next lecture, we will cover a couple of different approaches that are currently being explored to evaluate methods used to generate explanations. Stay tuned and see you next time.